In the last class, I had talked of comminution and grinding of ceramic powders. These are processes which are normally used for materials obtained from nature, but many of them are also used for grinding of synthetic powders. In today's lecture, I shall start on synthesis of ceramic powders from the precursors. You see, we do use single component systems like say Al2O3, but we also use two component systems like say barium titanate, nickel ferrite, more complex systems like lead zircon titanate. So, here I have a single component system, I have here a two component system, here I have a three component system, and the list can increases to 4 and 5 component. When do we need to synthesize ceramic powders? Let me take a very simple example like say the igniter you use in your kitchen. The active device is a piezo device which is based on lead zircon titanate. If you bother to take that open when it goes bad, you will see it's colored black. Well, it is black due to presence of impurities. But when we are using the same lead zircon titanate based ceramic for applications like say in sonars, in position actuators, in defense or in space, we require very pure lead zircon titanate, because the presence of impurities not only creates problems for sintering, but also alters the electrical characteristics. In such cases, what we have to do is synthesize them from the precursors. There I will be covering quite a few of the processes, but today I shall be focusing on solution growth of these complex oxides. Let me take the case of barium titanate. Barium titanate can be made by taking barium nitrate, which can be purified to 6N purity, that is 99.999%. Titanium tetrachloride, again 6N purity, 99.999%. All of these materials, whether it is barium nitrate or titanium chloride, you would take the case of nickel ferrite, which I had written over here, we will take high purity nickel nitrate, we will take high purity ferric nitrate, and then try to synthesize this powder. If I say take the case of barium titanate, the barium titanate was first synthesized by the Germans back in 1940s for fabricating multilayer ceramic capacitors. What they did was they followed a solid state route. That is decomposition, and reaction in solid state. Before I go on to precipitation techniques, let me focus on this solid state reaction route, because at times this is the only route available to us for reasons I will state later. What was done by the Germans back in 1940s was they took barium carbonate and took titanium dioxide and mixed them physically. Now I'll go coming back to the explanations a little bit later. After this, they heated it to 1300 degrees centigrade. When barium carbonate decomposed to give barium oxide plus carbon dioxide and titanium dioxide, and this barium oxide and titanium dioxide reacted to give barium titanate. Theoretically, this was the process. However, in real process, it had many unit operations, like say barium carbonate plus titanium dioxide, mix, heat to 1300 degrees centigrade, cool, crush, again heat to 1300 degrees centigrade, cool, heat, I've heated to 1300, so it is a cooling step here, crush, and this is repeated at least once more, heat again to 1300 degrees centigrade, cool, and then crush. You see, there were so many added unit operations. One heating step, cool, crush, second heating step, cool, crush, and third heating step, cool, crush. This is an inherent problem of solid state reaction. The reason is simply this. If I have got here the barium carbonate which I have taken, they normally have a particle size in the range of 100 micron to 500 micron, while the titanium dioxide is normally less than 100 micrometer. When barium carbonate is heated, we conveniently write it forms barium oxide plus carbon dioxide. In reality, what happens is far more tougher. This is the barium carbonate grain. And heat is supplied to it. What happens is from the surface layers, barium carbonate at the surface layer, they decompose. Over here we get BaO plus CO2. The CO2 escapes. Now this goes on very conveniently up to a few monolayers. So what we have is a few micrometer thick area where we have got BaO and CO2 has escaped. However, look at the situation inside over here. This grain will also liberate CO2, but then as the CO2 tries to go out, it reacts with the BaO layer over here. So this grain dissociates to give you BaO. The CO2 tries to escape. There is a BaO there, it forms barium carbonate. This particular layer has to decompose, liberating the CO2. The CO2 goes out and is again absorbed to the next layer. So what happens during these steps as we go deeper and deeper in? Diffusivity of CO2 to outer atmosphere decreases. So it is not that this particular grain will, which was BaCO3, if I heat it, it becomes BaO. This does not happen. What normally happens is that the outer layers form BaO, while this is the BaO is formed in the outer layers, while the internal layer stays BaCO3. The only way to expose this inner layer is to crush it, so that I have got and the grain now breaking up. This is the BaO layer, while the rest is BaCO3. The carbon dioxide can escape again from here. That is one reason why this repetitive process of heating, cooling, crushing was done. In those steps, those two steps, the grains were being broken up to expose fresh surface, so that the BaCO3 could effectively dissociate and the grain was converted to BaO. The second reason is this. Let us again go back, presume that I have got BaO around here, BaCO3. I have got BaCO3 grains. And I have titanium dioxide. I have titanium dioxide grains out here. The red grains are all titanium dioxide. So when this is heated, what would happen? Carbon dioxide would go away from the outer layers, leaving the BaO layer. This titanium dioxide would react with these BaO layers. And as a result, not only has the diffusivity of carbon dioxide been reduced due to formation of BaO over here, what has happened more is this, that a new layer which was formerly BaO, that has reacted with the titanium dioxide to give you BaTiO3. This BaTiO3 is very, very dense. This is a very, very dense layer, and hence removal of carbon dioxide from inside is virtually stopped. It cannot happen. So, due to this reason, in the solid state reaction route, just like the Germans had to do, we have to repeat unit operations like heating, cooling, crushing, and again heating, cooling, crushing, so that we could crush these grains, expose fresh surfaces, which would react with the TiO2 all over again. Now, the problem with this particular process is, while this is possibly our last fallback in ceramic synthesis, when nothing else works, this is what will work if we take care. But the difficulty of this process is that we have to crush the particles. Now, I had talked of in the earlier lectures of contamination. Whenever I took a milling operation, that is, this crushing which I talked of was really crushing milling by milling, there is a fear of contamination. Here we are starting off 99.99% pure powders, and when we want massive productions, if we go to crush it, there is a problem of contamination. And so, this is the last option that we have very frequently, but this is an option we want to use only when our backs are to the wall. However, in this solid state reaction route, let me say today, how would I teach an UG student how to make barium titanate by the solid state reaction route? What I would do is, instead of barium carbonate, I would take barium nitrate and titanium dioxide. I mix them and fire them. if they are heated at 1150 to 1200 degrees centigrade, you get barium titanate straight away. Unlike in the case where I had used barium carbonate, I had to undertake 3 unit operations. Here a single step is sufficient to give me barium titanate. And the reason is very simple. The reason is most of the nitrate salts, when heated, they fracture. So when this barium nitrate is heated, it breaks up into very fine pieces. As a result, generating fresh surfaces, and the reaction of titanium dioxide is very fast. We at times today in the laboratories, we prefer to prepare barium titanate using nitrate route because it's a single step process. Yet even here at times we have inhomogeneity, which is a problem with the solid state reaction route. I talked of nickel ferrite earlier at the start of the lecture. Yes, it can be made by mixing nickel oxide with iron oxide and firing. Ferrites have been here around since the end of the First World War, mid 20s in industrial applications. People did use the solid state reaction route. But today, when sizes are coming down, when it is very imperative that the losses be minimized, power be maximized, it is very essential for the nickel ferrite to be much purer than what was used say in 1920s or 30s. So in such cases where we require very pure products, we try to look for routes where crushing, grinding, milling, repeated heating are avoided. One of the ways you might say is, why don't you take nickel nitrate, iron nitrate? Let's say the question might come is, why don't you take nickel salt, take iron salt, dissolve them in equimolar amounts, dry the solution, and then fire to get the mixed oxide. The problem is, over here when I am dissolving them in equal equimolar amounts as solution, yes, the nickel ions and the iron ions are mixed at a molecular level. But as I try to dry the solution, differential crystallization occurs. That is, one of these salts crystallize out earlier, the other one separates out later. So in this particular step, we do not have a molecular level of mixing. It is a very inhomogeneous level of mixing. At times it can happen that one salt has crystallized out much before the other one has. So in the earlier stages, what people did was, they would take, let me say, a metal M1 salt add to it an metal M2 salt, dissolve them, mix equimolar amounts, let us say I have got M1 N plus, I have got M2 N plus in solution. The easiest thing to precipitate them would be, let us say, if we add hydroxide, say as ammonium hydroxide, drop by drop. To get M1 OHN, M2 OHN in molecular level of mixing. Unfortunately, this does not happen. And the reason is simply this, that when alkali is added, alkali or NH4OH is added, and we get M1 OHN and M2 OHN, they have a solubility product. It is not as if they will immediately precipitate. This M1 OHN will ionize to give you M1 N plus plus NOH minus in solution. M2 OHN will dissociate to give you M2 N plus plus NOH minus in solution. If we look at the solubility equation, let me take for example the case of say silver chloride. This will dissociate to give you Ag plus plus Cl minus. If I try to dissolve silver chloride in water, KSP is a solubility product which is basically a multiplication of the activity coefficients of silver ions and chloride ions that are in solution. It is not that all silver chloride is dissolving, a very small amount will dissolve, and that silver chloride will ionize. The solubility product of silver chloride is given by this reaction. Now, if I look at say in the case of the metal ion M1 OHN, the KSP can be, let me pick up two numbers, 10 to the power of minus 8, whereas for M2 OHN the KSP can be 10 to the power of minus 22, let us say, widely varying. This means that in this solution, when I add alkali, the first thing to be precipitating out is M1 OHN. M2 OHN will not precipitate because the alkali will be first consumed by M1 ions to form the hydroxide, and until the M1 ion concentration has fallen sufficiently low, M2 OHN will not precipitate. So, in most of the cases, if we take say a solution of two metal ions in solution and then add alkali to it, we do not have the ions precipitating together. In most of the cases, it is one of successive precipitation. as I have just said here, because the KSP is 10 to the power of minus 8, M1OHN will precipitate first. This is successive precipitation, and this does us no good. What we really need is co-precipitation. That is, the precipitate will be a mix of M1 OHN and M2 OHN at the molecular level. Before I go on any further, because when I am talking of co-precipitation, I am taking on an entirely different new concept. I have to first talk of nucleation and growth from solution. Most of you have seen sugar. You have bought sugar in the market. You have seen sugar cubes which are very coarse, each side couple of millimeter, 2 millimeters. There is sugar which is very fine. Both the coarse and the fine sugar has been generated from the same sugar cane. What they do is take the sugar cane, heat it to a certain temperature till a certain step has come, and then cool it, and the crystals separate out. You see, in a sugar cane, when I am talking of crystallization of sugar from sugar cane, it is called homogeneous crystallization. That is, I have a container with clean side walls and a solution which is clear, no suspensions present. It is a very clear solutions with no suspension present. When the, let me take up a diagram. Let me take the case of the sugar cane itself. On this axis I have plotted the time and this concentration of sugar. At 0 time I have got the standard sugar cane and the concentration of sugar is, let us presume, somewhere over here. What they do? They then heat it. As it is heated, water starts evaporating. If you keep on heating, what will happen? Water will start evaporating, will keep on evaporating until such time the solution becomes supersaturated with sugar. That is, the sugar cannot be held in solution anymore because the volume of the water which is available has reduced. So, if I start off from this point of time, I am heating the sugar solution, the concentration of sugar rises till it reaches a point of supersaturation. Let me label this as concentration supersaturation. At this point, if I keep on heating, what would happen? Sugar would start precipitating out. Why? because it is already supersaturated, the solution cannot hold any more sugar, it will come out. Now, let me hold the whole solution at that particular temperature and time when I have just reached supersaturation level. And let me do something over here. This is the temperature of supersaturation. I have got a supersaturated solution. Now, I drop the temperature down to this level. As soon as I have dropped this temperature down to this level, this is called the degree of undercooling, or del T. From this temperature, I have got it down to this temperature. Immediately what happens is, on this axis you can see that the maximum concentration of sugar which can stay in solution has decreased. So, now the sugar which was in solution over here has to precipitate out. What happens during this precipitation? That is, I have got a clear solution. This is supersaturated and I am now cooling it. What happens is, very isolated nuclei start separating out. This is the nuclei of the sugar, because I am talking of sugarcane, sugar solution. This nuclei which is first formed is very unstable, So, this nuclei dissolves and a bigger nuclei is deposited. This nuclei may still be unstable, this will dissolve and a bigger nuclei is deposited. This formation of the nuclei is dissolution and formation of a larger nuclei goes on. What happens is, I can draw a graph del GV versus radius of the nuclei. And the graph would be something like this. This is the critical radius RC. You see, up to this RC, it's a bit wrongly drawn graph. Anyway, the del GV has kept on increasing. So, this is a thermodynamically unstable situation. That is why the nuclei keep on dissolving. Only when this radius of curvature has been achieved do the nuclei start becoming stable. And at this point, these nuclei are stable. I talked of, as undercooling proceeds, what happens is, over here, this is the original nuclei, two things may happen. This is the original stable nuclei which is corresponding to this. Two things may happen. One is, this nuclei may keep on growing, which leads to large crystals. Or what can happen now is, this nuclei serves as a nucleation center and smaller crystals grow around it. And smaller crystals grow around it. While this is true homogeneous nucleation, this becomes sort of heterogeneous nucleation. Because here the nuclei are not growing, but rather this large nuclei which has got the required critical radius, around it smaller nuclei are depositing. I would rather call this a pseudo heterogeneous nucleation. A real heterogeneous nucleation occurs when, say, we want to have core shell structure. Means we have certain fine powders dispersed in a solution, and over here what we wish to generate is a layer of this solution, the material from this solution over here. The black part is a core, the blue part is a shell. This is a true case of heterogeneous nucleation. However, we are going to focus only on homogeneous nucleation, as we want to have powders which are co-precipitated. That is, component A and component B are co-precipitated from the solution at the same time. If heterogeneous nucleation occurs, I would never get co-precipitation. It would be a core shell structure. Now, one of the ways in which this, let me take the case of barium titanate, because that is I am taking that because it is referred to in books very frequently, is what the process would be to take, let me say, barium nitrate solution, let me say 0.5 molar, and titanium tetrachloride solution, let me say 0.5 molar, mix 100 ml of each to get a solution which has got both barium nitrate and titanium tetrachloride in solution. To this mixture, we add oxalic acid. What happens immediately when we add oxalic acid is a compound BaTiO C2O4 twice barium titanyl oxalato complex. This is formed. For those of you who are a bit not sure, oxalic acid is C double bond OOH, C double bond OOH. The very fact that this complex has formed means it has got a very large molecular size. If you remember, I had said critical radius is achieved, until critical radius is achieved, the nuclei are not stable. Now, here in this case, I have barium titanyl oxalato complex which has got a very large molecular size, and hence RC is reached faster. And hence what happens over here is barium, titanium are co-precipitated as very fine powders. Because the barium titanyl oxalato complex size is very large, the radius, critical radius is reached very easily, and hence we get very fine powders. The advantage of this barium titanyl oxalato complex is this, that when it is heated at temperatures maximum of, let me say, 700 degrees centigrade max, the oxalate molecules decompose and we get barium titanate straight away. We do that at much lower temperatures. The purity of the 6N, that is 99.99%, is maintained, and we get ultra pure barium titanate powder at much lower temperatures. Much lower temperatures means grains are still fine, they are ultra fine, and this has got its obvious advantages in subsequent processing and fabrication. Now, I took the case of barium titanyl oxalate because most of the books refer to it. Similarly, I can prepare NiFe2O4 also by oxalate method. However, this method, the oxalate method, cannot be used right across the board, because having complexes of both the cations by the oxalate is again a thermodynamically driven process. So far, oxalate process has been limited only to a few systems like, say, barium titanate, nickel ferrite. In other cases, when we want to synthesize a powder from solution, we have problems, because the hydroxides of the cations, they have got different solvent products. Let me take the case of magnesium aluminate, a very important ceramic material today for high-end refractory applications. It is refractory means not only bricks, but thermal insulation coatings. Magnesium aluminate is also coming in as catalyst support for conversion of carbon monoxide, nitrogen oxides in automobile emission, and this is a very, very high value added product. The KSP of magnesium hydroxide is different from KSP of aluminum hydroxide. So, the precipitation process is difficult by adding ammonium hydroxide. The magnesium aluminum oxalato complex is very soluble in water. So, unlike in the barium titanate case or the nickel ferrite case, oxalato complex route for making magnesium aluminate from magnesium nitrate and aluminum nitrate is not a viable option. One of the ways we make magnesium aluminate ultrafine powders is we take magnesium nitrate plus aluminum nitrate, dissolve equimolar amounts and then we do spray pyrolysis. If you do a image search, if you do a Google image search using as search term, you will see images of spray pyrolyzer, what it is. Unfortunately, I cannot show it because all of it is copyrighted. There are very few, there's only one reasonable picture of spray pyrolysis in open source. So I leave it to you to Google this Google image for spray pyrolysis and you will see excellent diagrams of spray pyrolyzers. What is done in spray pyrolysis? All of you or most of you have seen the oxyacetylene torch. This is used in say bicycle shops to repair your bicycle, broken parts, brazing, welding, a lot of it. What is done in that oxyacetylene torch? Acetylene and oxygen are fed in to a burner using two nozzles, one nozzle and this is the second nozzle. You feed acetylene through here, oxygen through here, they mix in this zone and then you ignite it with a flame. As a result, you have a long flame with a temperature whose temperature can reach anywhere up to 1800 degrees centigrade. This oxyacetylene torch is there in any machinist shop. When your bike has broken down or you have someone's bike has broken down, you have seen this torch being used to repair it. Now, what is done in spray pyrolysis is we can take the same oxyacetylene torch and feed in vapors of magnesium nitrate plus aluminum nitrate solution. In the form of very fine spray. These fine sprays will be carried through with the gases and there in this hot zone a lot of things can happen. For example, at the very first level, this is, let us say, a droplet of solution sprayed in. when the solution, when these droplets enter the hot zone over here, what can happen is water may evaporate from the surface and it gets smaller. As it gets smaller, as in the co-precipitation process, volume precipitation will occur and we will get finally a dense mass which has got magnesium nitrate and aluminum nitrate intimately mixed. The problem comes when we have, as the water evaporates, if we have surface precipitation. In that case, we have a major problem, because in the surface precipitation, the particles will start, because it is very supersaturated at the surface, will start precipitating the surface. And this may lead to two types of products. One is this type of product, highly dense, or this sort of a product which is very permeable and possibly inhomogeneously mixed. One of these two are possible. What we require is basically volume precipitation. If I take this volume precipitation itself, there are two options that is possible, depending on how long these fine sprays are resident over here. You see, even though I am firing this solution into a 1800 degree centigrade flame, so the temperature jump is very high, evaporation rate is very high, yet two things can happen. Co-precipitation of magnesium nitrate, aluminum nitrate can happen inside this particular one, or successive precipitation can happen. So, even though in this particular case of spray pyrolysis, we have injected very fine mists of solution of magnesium nitrate and aluminum nitrate, our degree of heating is very high, yet in some cases, if we are not careful, successive precipitation can happen. And in this case, what we will end up with, if I look at this, a microstructure where I will have one component on the outside and the second component on the inside. Though what we really need is the two components dispersed uniformly. So, even in spray pyrolysis, we have to be very careful as to how we go about it, because here we are merely relying on the fact that the water will evaporate first, our fear is we may have still problems over here, because you have to realize this is magnesium nitrate, aluminum nitrate is not what we want. We want MgAl2O4. I shall carry on with this in the next lecture.